All right, so like I keep losing my train of thought. It's very, very distracting when your lecture gets interrupted like this. Okay, so we're talking about the grocery store of one big task that is serving all the customers being broken up to 10 or 20 different things. All right, and that's an example of parallelism. Then we can think of other examples like the deli counter. Deli counter is a special example which is particularly interesting because in the deli counter, what you have is many workers serving many customers, but often the customers are ordered. Okay, so one thing you probably will have noticed is that the checkouts will, when you line up, you often think getting through faster. But with the deli counter, what happens is all the customers get ordered often. And the way that works is you pull a piece of paper, it gives you a number, and then when your number lights up on a screen, then it's your turn to get served. And what that's doing as soon as an ordering on all of the customers getting served. Unlike the example of the checkouts, where they're all doing it in parallel, but there's no real ordering there. And if you just accept it at each aisle, and so if you go to the wrong aisle, well, then things don't go very well. Then the next thing the thing about the deli counter, which is really interesting, is that actual example of using that piece of paper to put an ordering on all the customers is something we actually do in computer science, and we actually call it a deli counter. Okay, so if you think about that, so when someone's going to put your order and you say, I want some of this sliced stuff, I want some olives, I want some cheese or whatever, and then the next customer comes and so forth, and the multiple workers are serving multiple customers, but each of the customers are being done one at a time. Deli counter, and that's what that's a very important concept. Now let me move on. Okay, I want you to now think about a kitchen, and I want you to think about a very large kitchen in a really big restaurant. You've got lots of sous chefs, lots of people who are doing the jobs of the big shots. Okay, now I want you to think about a soup. And I want you to think about the very simple task of putting salt in the soup, which you have to do at a certain point. Okay? Now, the salt has to be put in. If you weren't sure about who was going to put it in, you'd want some mechanism to make sure that it got put in. If it didn't get put in, the soup wouldn't be good. On the other hand, if it got put in twice, the soup would be ruined. Okay? So you have to have this thing where you make sure that someone puts the salt in, but not two people put the salt in. So how do you do that? Well, the situation I'm trying to describe here is what we call in computer science a race condition. So a race condition is when you have multiple things trying to do the same thing at the same time. Okay, so and it's unclear how you ensure that exactly the right things happen. Another example you might have thought of, that there's a concept here which we call atomicity, and there's and you may have run into this when you think about getting money out of a machine. If you've used one of those machines and put a card in and get money out, what you want to have happen is when you say, give me the money, what you want to have happen is that you get the cash and basically exactly the same time the money comes out of your account. You don't want to have it happen that the money comes out of your account and then the machine goes, oh, sorry, we couldn't give you your cash. Now you've lost the money from your account, but you didn't get the cash in your hand. That actually happened to me last year. Luckily, the bank gave me the money back. But you want to make sure that that doesn't happen, okay? Likewise, the bank doesn't want to give you the cash and forget to take it out of your account. That would be bad. You want both of them to happen or neither of them to happen. That's a concept of atomicity. Now, let's get back to the salting thing. One way, the salting the soup thing. One way you could deal with salting the soup would be to one way of dealing with salting the soup would be to have like a checkbox, right? That says, okay, the soup has been salted. And then before one of the sous chefs goes to put the salt in, they check the box. But if you didn't do this well, if you did it in a silly way, you could still run into troubles. If you had the check box over on the wall of the kitchen over there and the soup was over there, you could have a problem because someone could go and put the salt in, then walk off and check the box. Meanwhile, someone else looks to see that the box is checked, notices it's not checked, then goes and puts the salt in. And in a busy kitchen, they may cross paths and you may still end up putting the salt in twice. Okay, again, that's what we call a race condition. I know it sounds slightly contrived and ridiculous, but this sort of thing happens very easily in real computers, which I'm going to demonstrate for you soon. Okay, so how would you solve that? Well, obviously a slightly better way of doing that in the kitchen would be to have the checkbox right above the pot, so you couldn't, so you actually did the checking the box and putting the salt in at the same time, and it wouldn't be the case that there was this moment where the salt was in but the box wasn't checked. Okay, which is the silly situation I just explained, which could lead to a possibility that the salt got put in twice, which would destroy the soup. Okay, so really what you want is this concept like with the cash machine of what we call atomicity, where the salt gets put in and the box gets checked at the same time. Now, so hopefully I've sketched for you a few examples. Let's run back over them again. The 7-Eleven store, lots of different jobs being done by one worker, cleaning up the floor, making the coffee go, doing the checkout, making sure the stuff on the shelves, all those things done by one worker. There's no concurrency, one worker. Then the large grocery store, which has the same jobs plus more, being done by maybe 20, 30 people at once. That has a lot of concurrency. It has concurrency between the person in the checkout and the person mopping the floor. It has concurrency between the checkout people. And then the next concept I wanted to emphasize for you is this notion of parallelism. The notion of parallelism is a special kind of concurrency where you're doing one task, one big task, with lots of workers. And the big task might be making sure all the customers get to pay for their goods. So if you've got 10 people at checkouts, that's conceptually one task, and 10 people are doing it. Or you're stocking the shelves, that's one task, but you've got 4 or 5 people putting the stuff on the shelves. Okay, that's what we call parallelism. I also want to make the point that why do we do parallelism? That speeds jobs up, right? So if we only had one person doing the checkouts instead of 10, then probably the customers would have to wait 10 times as long and they wouldn't shop at your store, right? Parallelism does not work for all tasks. And I want you to think about for a moment about why and examples of where it doesn't work. Okay, and I'll give you an example. If you've got a kitchen and someone says to you, I want you to bake a cake, and you're like, okay, cool, that'll be an hour and a half. And they're like, don't worry, I've got 10 ovens, so you can do it in 15 minutes, right? Of course, you can't bake the cake 10 times faster just because you've got 10 ovens. It doesn't work that way, right? So baking a single cake is not helped very much by parallelism. Having 10 ovens does not get you anywhere when baking a single cake. On the other hand, if someone said, I want you to bake 50 cakes for a bake sale, and here's 10 ovens, then you can probably do that baking about 10 times faster. Okay, so it depends entirely on the problem. Some problems are not amenable to parallelism, like baking a single cake. Other tasks, like baking 50 cakes, are absolutely amenable to parallelism. So there's a whole question about what works with parallelism and what doesn't. And one other thing I want to show you is that there's a lot of parallelism going in on my computer right now, even if some of it's misbehaving, like OBS. And what we can see that if we go here to the activity monitor, and we have a look here, and we can see OBS is a little bit unhappy. It's using 95% of my CPU. And it's got 34 threads running. See, look at the column that says threads, right? So OBS is really busy. That's the thing that's making the video that you're getting on the stream, which apparently is working at the moment, but wasn't before. And you can see there that it's got a lot of threads. Notice also that Chrome is using a stack load of threads. That's just the web browser. If you go to the web browser, what have we got here? Okay, I was checking the speed, but only one tab, right? I've got one tab open, and it is doing, look here now, it's still got 34 threads or so, even more. Even the Stream Deck, that's this little gadget I've got here to change my OBS settings. It's a little tiny gadget with a USB connection. Look at it, it's got 36 threads running. Okay, these things are using lots of threads. Those threads are conceptually what we call workers. Okay, so you can see here, if you look at how many threads are on my computer at the moment, you can see an IntelliJ, look, it's got 48 threads. You can see on my computer at the moment, there's hundreds, literally hundreds of threads running at the same time on this computer. Okay, and that's interesting. But the thing is, this particular computer, I think, only has 4 cores on it. So it's got basically like 4 computers on this machine. We call them 4 cores. It's got 4 cores. So somehow or other, the operating system is making these 100 or so threads fit onto 4 CPUs, which is really interesting. Okay, so it's using there's a whole lot of interesting stuff about how that works. So in fact, there aren't actually hundreds of things literally happening at the same time. At any moment in time, there's actually only 4 things. Okay, so yep.
We got several questions from from student. Alan asked, does concurrency work in single core systems as well? And Joshua asked, can each thread only do one thing?
Yeah, great questions. I'm so pleased that we actually have questions coming. So the first question was, oh, hang on, can you repeat the question? I was overwhelmed to actually hear that we're getting questions. I'm sorry, what was the first one?
Does concurrency work in single core systems?
Yeah, great question. Does concurrency work in single core systems? Yeah, it does. It's really fascinating because what can happen in a single core system, what you do is you've got all these different jobs and the computer underneath, we don't control this unless you're working the operating system. What it does is it keeps swapping what's running on each core at any moment in time at a really, really fast rate. Fast enough that you can't even notice as a human, right? So it just keeps switching, which is how you got those 100 or so things running on this 4-core system. So if you had a 1-core system, which I don't here, you might still have 100 things and they're all running one after the other. The thing is, you get what looks like concurrency out of that, and a lot of the problems we face with concurrency, which we're going to talk about more in a moment, can still arise even in the single core system because if you think about it, the silly example with the chefs or whatever, you can imagine that you stop, one chef, the one who goes and adds the salt, now he's going to walk across and check it off. Okay, now they stop working because you've got only a single core. The other one starts working, sees that the thing's unmarked, and then starts walking to salt the thing, and then maybe they get stopped and the other one runs and so forth. You can still get exactly the same problems happening even if they're sharing the resource. Okay, so I don't want to go into that too much. It's a great question, and so it's a really interesting question. I'd love to talk about it more, but we don't have a huge amount of time, and it's actually way beyond what you need to know in this class, even though it's a cool question. What was the second question from Joshua?
Can each thread only do one thing?
That's a good question. What can a thread do? What is a thread? I'm going to talk about that more concretely in just a second. I think on the very next slide. So why don't I answer that then? Okay, so yeah, at the bottom of the slide, I kind of answered that question, of Joshua's question. Okay, so what is concurrency? So I talked with a lot of hand waving and analogies. Now, let me say it slightly more formally. Concurrency is when multiple activities, and notice this is for the first question, it says appear to, that's because it may actually be only a single core. So appear to happen simultaneously. So record this lecture, if it's actually working, and displaying the slide. Okay, so the slide is happening and OBS is doing its stuff. They appear to be happening simultaneously, okay? Time slicing, and this is the answer to the first question, allows a single execution unit to give the appearance of concurrent execution, okay? So it can look like there's concurrent execution when there's actually only one resource, okay? That's like a single worker in the shop changing jobs all the time, right? Just running around and doing all the different jobs, like the 7-Eleven example, okay? And then the process, okay, what is a process? A process, these are terms. Process and thread are important terms. A process is what we call a distinct execution context that by default shares nothing. So you can think of IntelliJ as a process, PowerPoint as a process. One instance of IntelliJ is a process, one instance of PowerPoint is a process, and the video recorder like OBS is another process. And then a thread is something that runs inside of that. It's concurrency within OBS, concurrency within PowerPoint, concurrency within IntelliJ. Okay, and they share stuff so they can all see the same memory. But between the processes, they can't see memory unless you do something special. Okay, so by default, they don't share anything. All right, so that's what a process and a thread is. And I'll just go to, I think I'll just open up the mini quiz now, or no, we got more here. Yeah, so why do we use threads? Okay, we use threads for two reasons, and hopefully you've got this idea now because hopefully you understood my analogies. A concurrency is when you want to separate concerns, for example, rendering and logic. Oh, this is an interesting question. You may want to think about where concurrencies happen in class so far. I'm going to leave that as an open question. I'm going to let you try and answer that. So have you seen any concurrency in this class already? Even though we're only introducing it at the end here, I think you'll find that we've actually had concurrency going on under the hood. And if you can think about what that is, let Leo know and I'll respond. Okay, so concurrency is good for separating concerns. You can do one thing over here, another thing over there, and it's good for distinct tasks that occur concurrently. And the examples of the grocery store make it very clear. You can think about other examples in your game or whatever where you might want to have thought about concurrency. This thing needs to happen, but that thing also needs to happen, and really they could happen at the same time. Parallelism, as I said, is a special case of concurrency, was where you break a task into pieces and you exploit the fact that you've got multiple workers, you've got parallel hardware. And so it's good for computationally intensive problems that can be readily partitioned. So it's good for the checkout thing, it's good for the bake sale, but it's useless for baking a single cake. Okay, so it depends on the problem. And with that, let's open the poll. Oops, not quite ready. Everything's not going to plan here. Okay, you should be able to see the poll now, I hope. And let's move on to the very last unit of the entire course, which is now taking those concepts I just talked about in a fairly loose way and applying them very concretely to Java. And we're going to do a really cool little example in code. So hold on for the example. I think you'll find that interesting and should make some of these ideas really concrete. And I apologize again, we're going to run over time because of the technical issues at the start of the lecture. And let's get on with this. So, did anyone have any answers about where we've seen Java threads, even though I haven't introduced the concept till J16? There's a hint. This has been happening under the hood since about week 3, I think, or week 4 or something. Anyone got any suggestions?
Alan asked, Alan answered, he suggests event handler in JavaFX, but he's a bit confused, so he asked, was that concurrent?
Yeah, exactly. Event handling in JavaFX is a great example. Okay, so that's exactly the one I was hoping you might guess. So event handling in JavaFX. So in fact, under the hood, JavaFX has a thread which deals with event handling. Okay, that's not clear. The way that presents the API, you don't know that, but that's what's going on. So there's a thread there which is listening for the mouse movements, that's listening for the keyboard things, and then sending messages. Okay, and so threads are actually going on when you use JavaFX. Okay, even though you never saw that in the way we taught JavaFX and the way it's explained in the JavaFX manuals. Under the hood, that's how it's working. It's using threads. So that was a really great suggestion, and that was what I was fishing for. Yep. Okay, so let's go. Sorry, Leo, did you say something? Nope. Okay, so there's a thing called thread and there's a thing called runnable. Thread is a class that we can use to create threads and interact with them. And there's 2 ways to create a thread. One is we can subclass the thread class. Okay, so we can make a new class which inherits from the thread class. And when we do so, we extend the run method. Okay, what's the advantage of this? Well, we inherit all the methods that come with the thread class, which is cool. The disadvantage is you can't subclass anything else. Why can't you subclass anything else? Does anyone know the answer to that? The other way you can do it is to use an interface, and that is we use the runnable interface and we implement the run method for the runnable interface, which is very general. It allows us to subclass something else, but it does not inherit the methods with threads, so you lose some of the power of the threads methods. Okay, so this is a choice. So this is a trade-off. This is not a big deal, but I would like you to see if you can remember or imagine why we have to make this choice in Java. You've either got a subclass thread, which means you can't subclass anything else, or you use the interface and you implement the runnable interface, and then you don't get the methods that you would have otherwise inherited from thread. Did anyone have any answers to that? As to why we have to make this choice between the 2 different approaches? There's a very simple answer which goes back to really early on in the lectures. It's a basic property of Java, which is arguably a good thing. Any suggestions? The answer is, here's the answer, spoiler, the answer is Java has single inheritance. So in Java, you can only inherit from one thing. So if you're inheriting from thread, if you make a class that inherits from thread, it can't inherit from something else. So if you make a dog class that inherits from thread, it can't inherit from mammal as well. It has to be one or the other. Okay, so you can't inherit from 2 things. That's just a fundamental property of Java. So if you wanted to make your dog class have threads, then but it's already inheriting from mammal, say in our old example from early in semester, then you're going to have to use the runnable interface. And so you're going to have your dog inherits from mammal, extends mammal, and implements the runnable interface. Okay, so that's where you have the choice. Then 3 methods that you really need to know about. There's a start method, which unsurprisingly will start the run method of the thread. So it starts the core of the thread, which is the run method. And when you call join, it will cause the thread in which it's called to wait until thread T terminates. So calling thread T start will start thread T, start the run method in thread T. Calling t.join will wait for this thread. It will sit and wait until thread T is finished. Okay, so they'll join each other. If you want to think of it a bit like one of those Git graphs, so starting, now you're running in parallel, and join, you're back in one thread again. Okay, so starting is starting another thread, so you're in parallel, and joining brings it back together again. So it's like a branch if you want to think of it that way. Okay, and then a sleep is a way we can stop a thread for a brief amount of time, pause a thread. Okay, so it'll pause the current thread, making it go to sleep for so many milliseconds, and you can change the number of seconds that it pauses for. Okay, we talked about the cooks and the salt and all that sort of stuff. The synchronized keyword is really important in Java because it allows us to solve that problem that I raised about race conditions and the example I gave with the chefs and the salt. Okay, so coordination is a big challenge for concurrency. So how do we avoid conflicts? How do we impose some level of coherence and order? So you don't want your salt in the soup twice, right? How are we going to do this? Well, a race condition is a situation where one or more threads race non-deterministically to be the first to read or write a variable. And again, it's a bit like the two chefs going to put the salt in and not being clear about there's putting the salt in, there's checking it off. It's two different things that need to happen. And if you're unclear about who's doing what when, then you've got a problem because you can end up having the salt put in twice, okay? And a synchronized keyword means that the whole operation happens entirely or not at all. Only one thing can do it at a time. So if you made check off the soup and salt it synchronized in Java, it means that only one chef can salt the soup and check it off. There's some constraint that makes it impossible for anything else to happen. So that means that if anyone decides, I'm going to do the salt, as soon as they pick up that spoon to do the salt, no one else is allowed to pick up the spoon until it's been checked off. And then the next person who comes along will look at the thing and say, oh, it's already been done. And you won't have this race. Okay, so the synchronized keyword is a way of grabbing multiple things in a method and saying everything in that method happens all at once. We can't have two threads doing this at the same time. So this is a really valuable way to address the possibility of a race condition. Otherwise, you could have two things running the same method at the same time, which could cause chaos. Okay, so the synchronized keyword is something we use when we know we've got something where we can't afford to allow this to happen. Okay, a mini quiz time. And here it is, the last mini quiz of the year. Any questions there, Leo? Nope. All right. I hope I haven't lost Leo there. All right, what I'm going to do now is we're going... Good. No questions. Okay, so we're going to finish up, folks. There's the last bit of code for the year. We're going to finish up by creating a class here and doing an example of concurrency and a race condition and solving the race condition, okay? So what you're going to see here is a race condition, and then I want you to think about how we're going to solve this. And now we're going to call the class worker. Worker or woker. We're going to call it worker. The idea being that the worker is someone who's doing a concurrent event, okay? And so this is a class called worker. And what we're going to do is we're going to get worker to implement runnable. Remember, if we want to have multiple threads, we can either implement runnable and make a run method, or we can extend the threads class. So we can say extends thread, or we can say implements runnable. Like that, okay? And now, of course, IntelliJ is saying we want to implement these methods, and we'll say, sure, go ahead. So implement the methods, like that. Now we have a run method. What goes in this method here, the run method, is the stuff that we want the thread to be doing. So if we wrote a loop here, we'd sit around and do this loop until something happened. All right, that's the stuff that's going to happen in parallel. And somewhere else, we're going to say, hey, create a thread and run it, okay? So now let's go and write some code. The first thing we're going to do here is something a bit silly. We're going to have a whole lot of workers trying to solve a very simple task, okay? So I've got a pile of tasks. I've got like 1,000 tasks that need to be done, and I'm going to have some number of workers, maybe 4 of them, and they're all going to try and solve that task as fast as possible. So there's going to be 1,000 jobs to be done, and each of the 4 things are going to grab one of the jobs, do it, and then grab another one, okay? So they're all racing to grab the next job off the stack, okay? So it's a big pile of jobs, and they're all going to try and work through those 1,000 jobs as fast as they possibly can, okay? So, so now let's write a variable here, work item. So we're going to number which work item it is. So the work item is which number in the stack it is, work item, okay? And we're going to initialize that to 0. And then we're going to have some constants. So say static final int work items. That's how many items we've got. And we're going to have 1,000 of them, okay? 1,000 work items. Whoops, 1,000. And then we're going to have some number of workers. And we'll have 4. We could have any number here. If we have 1, of course, then there's no concurrency, okay? That's the definition of concurrency, is when you've got multiple workers. And 4 is a good number. It's not a lot of workers, but it's enough that it can cause chaos if things go wrong. All right, now what we're going to do is our workers are actually incredibly lazy. The task they're going to do is nothing. They're not going to really do anything. They're just going to sleep because they're lazy. So we're just going to write a little method here, which is their working task. Private void pretend to do work. So this is the job they're going to do for each task. So every time they get a task, they're going to do this thing, and it's going to be nothing because they're lazy. And we're going to use this method here. And they're going to sleep for 1. Okay, I misspelled thread. There it is. So they're going to sleep for 1 second. Okay, now this could throw an exception, so we need to wrap this. Hang on. Whoop. Yeah, do we want to surround it? Yes, we do. Okay, we'll let IntelliJ do that for us. It can throw an interruption exception. No big deal there. We just surround it with that try-catch clause. Okay, so now we've got a little thing here which sits and does nothing, okay, for 1 millisecond. So it's 1 millisecond. That's a unit of time that's going in there. So you can see it says millis. So it's number of milliseconds. All right, now what we want to do is write our run method, okay? And now we're going to have a little variable here called my task. That's the task that this one does. Remember, there's going to be multiple threads. Each one will be running the run method, okay? And when you create the thread, it'll have its own run method, and they'll be grabbing work items and and incrementing their own count. Okay, so we'll just do this int my tasks equals 0, like that. So they've got 0 at the beginning, and then we'll say my work item. It's whichever one they picked off. So maybe they picked off work item number 300, then they pick off work item number 317, and so forth. Okay, so they're going to have whichever work item they've got there. And then we're just going to say this. We're going to say while, and we're going to say my work item equals work item plus plus. That's this one. Okay. As long as that there is less than the total, is less than work items, we'll keep going, okay? So they're all going to race and try to increase the work item. They're going to increase that guy, and until they run out, okay? So they're all basically grabbing things off the work pile, if you want to think of it that way, okay? And each time they grab one, they get its number. So it's number 300, and it's number 301, number 302, and so forth. That's the work item, and they're incrementing work item, okay, which is this thing here. And then whenever they get one, they say pretend to do work, so they do some stuff, you know, solve the problem, whatever it is. Obviously, this could be real work. If we did a proper thing here, it could be, I don't know, any job you can think of, serve a customer, whatever, some piece of work, okay? But here we're just doing nothing. We're just going to sleep for 1 millisecond. And then they're going to count up how much stuff they did. Okay, my tasks gets incremented. Okay, so this is great. And now we're going to print out how much they did, s out. And we'll say thread, and we'll say there's a method here which allows us to find out the name of the thread. You can give threads names. So we're going to give the thread a name, and we'll say this thread, and then we're going to say how much it did. And then how many tasks it did, my tasks, right? And the idea is, of course, that all do about that. There is a race here, so it's possible that some will do more tasks than others, but they should all add up, right? So like that. Okay, so there we are. They're going to do that. This is all very simple so far. And then what we're going to do is going to write a main method. like that. And then what we're going to do is we're going to say, we're going to create a worker first. Worker, worker equals new worker, like that. Okay, so now we've we've created a new worker. So we've only got one worker, okay, one worker type, okay. We perhaps could have called this workers to be a bit clearer. And then what we're going to do is create a thread. So we say thread equals new thread, and then we'll give it a name. We'll call it. Actually, before you give it a name, you've got to. I think, yeah, we've got to say. Actually, when we create a thread, we pass it the instance. That's the instance there that is runnable. So we'll say worker, and then we'll give it a name. Okay, and we'll call it worker1. Okay, so there it is. Okay, so we've created a single thread. All right, and then what we're going to do is going to start that thread. Okay, so in the main method, we created an object called worker. We created a single thread, and now we're going to call start, and then we'll print out all done when we're finished. Okay. And I want you to think about what's going to happen here. If anyone, I don't know if you're still online, how much lag you've got there, but if you can think of what's going to happen here, it'd be really cool. Being the last lecture of the year, it'd be really cool if we had some more interactivity. So what do you think is going to happen when I run this? Okay, it should be going through the stack and doing, there's only one thread, okay, in the first example. We're going to make 4 threads in a minute. But at the moment, there's only one thread, and it should be going through the stack of 1,000 work items, and it should print out how many tasks it did. So I want you to think about how many tasks it will do, given that there's 1,000 work items, right, 1,000 of them. And at the end, it should print out all done. So I want you to think about what's going to happen when I run this. And if anyone's got anything, I'll get Leo to shout it out to me. Okay, it's running.
Joshua said it would do 1,000 tasks, which is sleeping for 1 second.
Right, and it did. It did 1,000 tasks, but look what happened that was weird. It printed out all done before it printed this out. Okay, it printed out all done, and then it printed that out, which is really weird. Why would that happen? And the answer is this, that we forgot to do a join, okay? So if we want them all to finish together, we do a thread.join first, and then we do all done, okay? I believe, yeah, okay, so let's just add, now join can throw an exception, so we'll surround it with a try catch. That's one of the things that join can do. It can be interrupted as well. So what's going to happen is it'll start, then this thread will sit and wait until the thread is done, and then it will say all done. Otherwise, what happened before was it said all done when they hadn't actually all done. All right, so now let's run this again. This time it should do, worker1 should do 1,000 tasks, and then after it's finished, it's say all done. All right, in a moment, the next thing we're going to do is make, okay, all good. All right, so now what we're going to do, we're not going to change any code except we're going to make multiple threads. I want you to think about what's going to happen when I run this with multiple threads. Okay, while I'm typing the code, try and write in the chat what you think is going to happen when I run this with 4 threads. Okay, the only code I'm going to change is right here. I'm going to make this have 4 threads, and I want you to write in the chat what you think is going to happen. All right, so now let's go this. So I'm going to make this an array of threads instead of being 1 thread. And like this, and change this. Okay, so we're going to have 4 of them, and then we need to create them. So we're going to have that new thread thing in a loop. So for int I equals 0, I is less than workers, I plus plus. Then we're going to say threads I equals new thread worker. So you're going to tell it, give it the instance and what its name is, and we'll just call it worker plus I. Okay, so it should be worker 1, worker 2, worker 3, worker 4. All right, so we've now made 4 threads, and now instead of starting 1 thread, we're going to start all 4 of them. Again, if you can guess what's going to happen here, write it in the chat.
Joshua said it would be like each worker did about 250 tasks.
Yep. All right, that sounds pretty good. Let's have a look. So someone suggested that what's going to happen is you're going to, the keyword was about, so they're not all going to do exactly 250, but it'll add up to 1,000, right? And then here we're just going to join. All right, so I'll just run through what this code is doing. It's very, very simple. I can get rid of these curly braces to make it a little bit more concise. All right, so what we've done here is we've created 4 threads. There we've started 4 threads, and here we're joining 4 threads. Okay, and then finally after we've joined all 4 threads, we're saying all done. All right, so now let's run it and see what happens. Here we go. Moment of truth here. And look at that. Exactly 250 each. No, not. What's happened, folks? Can you see what's happened here? You should find this very disturbing. Let's run it again, okay? Put in the chat what you think's happened. I'll run this again. I'll run it a few more times while you all look in the chat and think about what's going on here. I'll scroll this down so you can look more clearly at all the code. That code there is the important code. And here we go. There it is again. And one more time. There's something not right here, folks. What's not right? Anything on the chat, Leo? What's happened, folks, is we've got a race condition again. We've got a race condition, just like I described with the salting and the chefs. And the race condition is here. That is our race condition. That looks innocuous, it looks harmless, but that is a race condition. Why? Because all of the threads are racing to increment this single work item. Remember, this single work item is a field of the single worker. So that there's only one worker object, one worker object. And there are multiple threads for the worker. We should call this workers, it'd be a lot better. Let me do that. Refactor, rename. I'll call it workers. That's unhelpful to call it worker. And we'll rename this the same to make it clear. Has anyone said anything in the chat about what's going on here? All right.
Yeah, so a student found that they are actually doing more than 1,000 tasks. And
well, okay, the spoiler, they're absolutely right. There's more than 1,000 tasks because if you add those up, it's more than 1,000. It's not 250. And what's going on here is this is the problem. That looks like it's a single thing, but it's not. This is a bit like your the other examples I gave with the money and the bank being debited. There are actually multiple things happening which you want to happen as a single thing, but they're not happening as a single event. In fact, what's happening here, when you do an increment, what really happens is someone grabs something from the memory, adds 1 to it, and then stores it back into memory. So that's at least 3 operations. Load from the memory, add 1, store it back. 3 operations. And if multiple threads come and do it all at the same time, one thread goes and loads it, adds it, stores it, but while it's loading it, another thread comes in and loads the same value before the other one stored it. So they're both, so this one reads 300, goes and adds 1 to it, stores back 301, right? Another thread comes in, but it races against the other thread and gets there and sees 300, not 301, because it gets in just between the load and the store and the add, right? So now it also sees 300. So what does it do? It loads 300, adds 1, stores it back. Now you've got 2 threads who both think they got item 300 and who both wrote back 301. So you're doing extra work. That's the problem. So how can we solve this? Well, we can write ourselves a very simple little method called inc work item. So let's just do this. Like this, and then we'll just say return work item plus plus, like that, okay? And we'll just use that instead. Okay, so the same work is happening, now it's happening in a method. That won't actually fix our problem. Let's just test it. Let's just test this. So All I've done is move that single piece there into a method on its own. And some of you might be thinking, why is he doing that? There's a good reason why I'm doing this. Run this again, same problem. Slightly less, the numbers are slightly lower, probably because the race is a little bit harder now because we're calling a method. So it's interesting, but it's basically the same problem. Same problem. How do I solve the problem now? Does anyone know how to solve this problem? There's one thing I need to do. Okay, then what I need to do now is I put the synchronized keyword here. I do that. What that does is it says that only one thread can execute this method at a time. Okay, only one thread can execute this method at a time. Let's see what happens now. Just added that one keyword, the synchronized keyword. And what do you got here? Okay, so you've got 2 over, 1 over, exactly the right, 3 under, exactly 250 on average. Okay, so exactly 1,000 tasks. Let's run it again in case you think that was a fluke. Same again, 3 under, 1 under, that's 4 under, 4 over, and equal. So we've got exactly 1,000 again, right? And run it again. Right, you see it again. One was 1 under, one was 1 over, the other 2 were exactly on. All right, so I hope you understand what's happening here. Let me just quickly recap what we did here. There's a really important and really interesting piece of example. We've got a worker instance, single worker instance. That's an instance of this object here. It's got a field called work item, okay? And that's going to count up to 1,000, okay? And what you had was 4 threads. You made 4 threads, okay? The 4 threads all use that same object. There's the object. They're all using the same object, so they're all attached to that same object. And we started all those 4 threads, and what are those 4 threads doing? Well, here's what they're doing. They're doing this run method, which is what happens when you call start. They're going and grabbing a work item, and they're doing some work, and then they're going and grabbing another work item, and so forth. So they're all racing to grab the next work item off the pile, okay? And what we did is we originally just had this work item plus in here, instead of that. Then we made it into a method. Still had the same problem. They're all racing, and some of them are, and you're getting double work because one of them's reading 300, adding 1, storing back 301. Another one gets in exactly the wrong moment, reads 300 before the other one's written back 301, and it also reads 300. It also adds 1. It also stores back 301. Now your count is screwed up. And you do that enough times, fast enough, you'll end up with everything getting just slightly out. Okay, and that's what we saw. We did end up doing, 1,020 or something like that with just a few too many items. Then what we did is we put it in a method, and we used the synchronized keyword. And without the synchronized keyword, do that again, we get the chaos. And that's because multiple threads are doing the same method at the same time. And as long as we've got the synchronized keyword there, okay, so we've got chaos again, right? And as long as we put this synchronized keyword back in, it means that only one thread at a time can execute that method, which means that we no longer have a race. Okay, so we've solved this race condition. Okay, and here you see 2 of them were over, 1 of them was under by 4, and the other one was right on, which gives us exactly 1,000 work items. And with that, we're finished. And let me go to our last bio. And our last bio is Anita Borg. Anita Borg was a champion of diversity in computer science, which is a topic close to my heart. And sadly, she died early with breast cancer. But they, subsequent to her dying, they created a foundation called the Anita Borg Foundation. And we have a Grace Hopper Celebration of Computer Science, which she helped found, which is sponsored by the Anita, which is very tightly related to the Anita Borg Foundation. Grace Hopper Celebration of Women in Computing was something I contributed to just a few weeks ago with a panel session. It's an amazing thing with multiple thousands of participants advancing women in computer science, which of course is an issue for computer science because computer science is one of the least diverse fields in all of science. And I'm pleased that we've got a fairly diverse class. So for those of you who are not white males, good on you. I'm a fan of diversity, and I'm a fan of Anita Borg and what she did for computer science. And with that, we're finished for the semester. The only lecture we have left is next Monday, and that's a revision lecture. Please make sure you go to Piazza and make suggestions on Piazza for what you'd most like me to cover in the revision lecture. Okay, and make your suggestions in the one thread rather than creating new threads. That'd be great. Okay, have a great weekend. Well done for finishing your assignments, and thank you for tolerating the technology.